All right, let's go ahead and jump into some more example problems about particle equilibrium. So last class we covered all of the lecture material for chapter 3. So we covered everything that we need to know about particle equilibrium, and we had two big takeaways from that lecture material. We said that for two-dimensional particles, our equations of equilibrium were simply that the sum of our forces in the x direction must be equal to 0, and the sum of our forces in the y direction must be equal to 0. So we said that for any particle in a two-dimensional problem, we had two equations that must be true. Two equations that must be true. And then we also covered the same information for 3D particles, and the only difference for a 3D particle is that we now add the additional equation that the sum of the forces in the z direction must also be equal to 0. So, this is our equations of equilibrium for 3D, or all three, whereas our equations of equilibrium for 2D are just the top two equations. So the first section in chapter 3 was just practicing drawing free body diagrams. So our first example problem that we're going to work is we're going to work another free body diagram kind of example. We are going to work a system of pulleys problem, and so we kind of get an understanding for how pulleys can be used to give us a mechanical advantage. We can use a system of pulleys to allow us to lift a heavy load using a much lower force than is required to lift that weight. So let's go ahead and jump into our first example problem. And it reads, a mass M1 is 10 kilograms, hangs from the pulley system as shown to the right. Assume all pulleys are massless and frictionless. What is the unknown mass M2 if the system is in static equilibrium? Okay, so here I have drawn the system of pulleys up on the board, and it may not look at it right from the get-go, but this is a particle equilibrium problem. This is a particle equilibrium problem. In fact, we have 5 different particles that we could analyze in this system. We have the mass M1, we have this pulley, we have this pulley, we have this pulley, and we have the mass M2. Now, just to make sure our nomenclature stays clear, I want to be consistent with your class notes, and I have labeled these pulleys as A, B, and C. Okay, so we have 5 different particles that we can use to analyze this system. Now, it's a very, very simple problem because, in fact, it's a one-dimensional problem. So we're going to see that when we start drawing free body diagrams. But every single particle only has forces acting on it in the vertical direction, in the y direction. If I define my coordinate system as x, y, all of the forces acting in this problem are in the y direction only. So if we want to start figuring out what mass 2 is in order for this system to be in equilibrium, we need to break this up into our particles, and we need to draw free body diagrams of each individual particle. Okay, so let's start with the easiest one. Let's start with mass 1 here, and we can treat this, like we said, just as a particle with forces acting on it. So if we draw a free body diagram of mass 1, which weighs 10 or has a mass of 10 kilograms, right? What do we have acting on this mass 1? We have 2 things. We have a tension. We have a tension acting upward from this rope, which I'm going to call T1. So we have a tension acting upward, which I'm going to call T1, and then we have the weight of the mass, which is going to be 10 kilograms times 9.81 meters per second squared. So we have the weight of the particle and the tension of the rope, and those are the only 2 forces acting on this particle. So this becomes a very easy problem to solve. We only have to apply one of our equilibrium equations, and our one equilibrium equation is that the sum of the forces in the y direction is going to be equal to T1, which is directed up, minus 10 times 9.81, which is directed downward, so it's negative, is equal to 0. This is a very, very simple problem to solve. We can see that this becomes that T1 is equal to 10 times 9.81 is just 98.1 newtons. So we know what the tension of that rope is acting at T1. The next kind of big conceptual jump that we have to make is we have to recognize that this rope, and I didn't draw it all the way here. This rope is continuous. This rope is continuous all the way from the top of mass 1 around pulley A, comes back down here, and then it's around pulley B, and then it comes back and connects to the ceiling. So that's all one continuous rope that wraps around pulleys A and pulleys B. Okay, so we're just going to go ahead and write that down. Let's go ahead and make a note here that we said that tension 1 is equal to 98.1 newtons. Now we're going to keep that in our back pocket, and now we're going to jump to our next particle. So we can say, okay, we just looked at particle, the mass 1 particle. Let's jump to pulley A, and we can do a free body diagram of that. While we could do that, what that's going to solve for is that's going to solve for this tension or this force acting on the ceiling. So if the problem had asked, what is the support reaction from pulley A on the ceiling, we could find that by looking at our particle equilibrium of pulley A. That's not what the problem asked for. The problem, in fact, asked for mass 2. So doing a free body diagram of pulley A and solving for the reaction on the ceiling, while it may be interesting to know, is unnecessary for solving this problem. So I'm going to skip pulley A, and I'm going to move to pulley B, and I'm going to draw another free body diagram. Okay, so if we start with pulley B here, so I'll go ahead and label this as pulley B. Once again, this particle is in equilibrium. The problem did not give us any mass of the pulleys, so we are assuming that the pulleys are going to be massless, or that their mass is negligible when compared to the mass of M1 and M2. So we can say that, M1 is 10 kilograms. We don't know what M2 is, but the mass of pulley B will be something very small as compared to 10 kilograms, as to make it a negligible mass. Okay, if that's the case, let's go ahead and jump into our free body diagram, and we can see that we have that tension 1, that continuous rope that we solved for in the free body diagram of mass 1, is also acting on pulley B. So if I come back to here, we have that tension 1 is acting on both sides of pulley B. So we have T1 is equal to 98.1 newtons, and we have a T1 is equal to 98.1 newtons. So we have two tension 1s, both directed upwards, acting on pulley B. Okay, now we need to make our next jump, and we have a second cable here. So I did this one kind of in green, but once again we have a cable here, which I'm going to do in blue, which comes down off the bottom of B, wraps around C, and comes all the way back up to the support at the ceiling. So this cable is acting downwards from its central position where it is located in pulley B. So now we have a tension 2, which is acting like this. Okay? Once again, this becomes a simple one-dimensional particle equilibrium problem. So this becomes the sum of our forces in the y direction is going to be equal to 2T1, which are both directed upward, because we have a T1 plus a T1, so we have a 2T1, minus a T2 is equal to 0. This is a simple algebraic problem to solve. We get that T2 is equal to 2T1, which we can plug into our calculator, and if we plug that into our calculator, we get that T2 is equal to 196.2 newtons. 196.2 newtons. So I'll go ahead and go over here, and we are going to label this on our diagram so that we have T2 is equal to 196.2 newtons. Okay, so we're getting closer to finding our answer. So we've analyzed mass 1, we've analyzed pulley B, and the next particle that we're going to jump to is we are going to jump down here to particle C. In fact, we're going to go ahead and jump to a combination of the system of pulley C and mass 2. So we can actually do that if we want. If we want to neglect internal forces that are acting between mass 2 and pulley C, we can consider them as a system, a grouping of particles where they have an internal force that acts in between them, but if we're not particularly interested in the internal force, we can treat it as a combined system and analyze it together. This is a tactic that we're going to do several times throughout this course, so it's something that we want to kind of get used to doing. So let's go ahead and draw ourselves a free body diagram, and once again, I'm going to draw myself a free body diagram of this entire system. There's no reason for me to split pulley C and mass 2 apart unless I was specifically after the tension in the cable that connects pulley C to mass 2, which I'm not. I'm only interested in the value of mass 2. Okay, so here is my system of particles between the pulley C and mass 2. So we need to start drawing on our free body diagram what forces that we have acting. And we have, once again, 3 forces acting all in the y direction. First of all, if I look at pulley C, I have that cable 2 acting upward on it. So once again, I have a tension 2, which is equal to 196.2 newtons. And I have another tension 2, which is also equal to 196.2 newtons. So we have 2 of that tension 2 acting on pulley C. Now, once again, we are assuming that pulley C is massless, or that its mass is negligible when compared to the mass of M2. So the last thing that we have to do is we have the weight of M2 acting on the system. So we have the weight of M2, which is going to be M2 times 9.81 meters per second is going to give, or meters per second squared, is going to give me the weight of mass 2. The weight of mass 2. Okay, so once again, we are in a one-dimensional particle equilibrium problem, so we just have one equation of equilibrium because we have no forces acting in the x direction. So our equation of equilibrium becomes that the sum of the forces in the y direction is going to be equal to 2T2, which are directed upward, minus 9.81 M2 is going to be equal to 0. That's going to be our sum of our forces in the y direction, so we can see that M2 is going to be equal to 2T2 divided by 9.81, and we know what T2 is. We solved for it in the middle of the problem. So this becomes 2 times 196.2 newtons, all divided by 9.81 meters per second squared. So I just plug all that into my calculator, and I will find that M2 is simply 40 kilograms. M2 is going to simply be 40 kilograms. So this is an interesting result. Go ahead and look at your lecture slides, or go back in the video and look at the diagram. This system of pulleys has what we call a mechanical advantage of 4. So if we were using M1 in order to lift M2, we only needed a mass of 10 kilograms in order to lift a mass of 40 kilograms. So we have a mechanical advantage of 4, meaning that our input force is multiplied by 4 by this system of pulleys. So that also means, because we can't just amplify force with absolutely no downside, no negative consequence, what the consequence is going to be is if I have a 10 kilogram weight that I'm trying to use to lift a 40 kilogram weight, the distance that 10 kilogram weight will travel will be 4 times further in order to lift that 40 kilogram mass. So once again, let's say if I want to lift the 40 kilogram mass by 1 meter, I would have to move that 10 kilogram mass downward by 4 meters. Does that make sense? I'm asking you in a YouTube video. I hope everybody understands that concept. Okay, let's go ahead and jump into our second example problem that we're going to work. This one's a little bit more complicated. It takes a little bit more thought when we analyze how to solve this problem. This one is a true two-dimensional particle equilibrium problem. So whereas the last problem was only one-dimensional, we only had forces acting in the vertical or the y direction. This problem, we're going to have forces acting in both the x and the y direction, so we're going to have additional equations that we need to solve. Okay, so let's jump into it. 2 AISI 1040 steel ball bearings are arranged in a container as shown. So AISI stands for the American Iron and Steel Institute, and that's a professional organization that has a lot of standards for different types of alloys of steel and iron. So for instance, AISI 1040 is going to have a specific carbon content, it's going to have a specific manganese content, and it's going to be a specific type of steel for the desired characteristics of that steel. The ball bearings have diameters of 2 inches and 1.5 inches. The density of AISI steel is 0.2834 pounds per cubic inch. The geometry of the ball bearings with relation to the container is shown in the diagram. What are the contact forces between the ball bearings and the walls of the container, and what is the contact force between the ball bearings? Okay, so let's go ahead and take a look at a diagram of what we have going on here. So we have some sort of three-walled container, and inside this three-walled container, we have these two ball bearings stacked on top of each other. They are in contact with, or the 2-inch ball bearing is in contact with the bottom of the container in the left side, and the 1.5-inch ball bearing is in contact with the right side of the container. This is kind of our general overview of the problem. So what we have here is we have two particles. We have the 2-inch steel ball bearing, and we have the 1.5-inch ball bearing. So we have two different particles, and when we said in lecture, is we said that for two-dimensional problems with n number of particles, in general, we will have two n equations of equilibrium that we can do. So in this case, we have two particles, so n is equal to 2. So in a two-dimensional problem, we will have a maximum of 4 equations of equilibrium. We'll have a maximum of 4 equations of equilibrium. How do we determine those equations of equilibrium for this kind of problem? Well, we're going to do it by drawing free body diagrams. In fact, we can draw up to 3 different free body diagrams for this problem. So let's go ahead and do that, because I want to talk about each of the 3 free body diagrams as we come up with them and how we can kind of analyze this problem. So the first free body diagram I'm going to draw is of the system of the two particles. Okay, it's going to be of the system of the two particles. So if each individual particle is in equilibrium, then the system is also in equilibrium. And I can actually analyze the system as a whole, and that entire system must also be in equilibrium. So let's go ahead and do that, and let's look at these two ball bearings together. So we can say that if I have the 2-inch ball bearing here, and I have, let's draw that a little bit more round. If I have the 2-inch ball bearing here and the 1.5-inch ball bearing here, let's go ahead and draw what forces that we have acting on this system. So I want to go ahead and be consistent with your notes here. So let's say that we have the first contact force with this point here, this location where the 2-inch ball bearing contacts the left wall of the container. I'm going to label as N1, normal force 1. Okay, and then this contact point where the 2-inch ball bearing is in contact with the bottom of the container, I'm going to label as N2. As you remember from physics and probably from other parts of this class, remember that our contact points are always normal to the surface where they contact. So in this case, we have a vertical wall, so our normal force 1 is going to be normal to that, so it's going to be horizontal. Whereas here, the floor is horizontal, so the normal force is going to then be vertical. Okay, finally, we have one more contact point. We have the contact point where the 1.5 ball bearing contacts the right side of the container. So we can have one additional normal force, which is going to point back this way, which is going to be N3. But that is not all the forces that we have acting on the system. In fact, the problem gave us the density of the ball bearings. It gave us the density of the ball bearings. So that's a good hint that the weight of the ball bearings is going to be important. So since each of these ball bearings also has a weight, we can say that we have an additional force here, weight 1 acting down on particle 1, and we have weight 2 acting down on particle 2. So there is our free body diagram of the entire system. So this is going to give us 2 equations of equilibrium. We have the sum of the forces in the x direction is equal to 0, and we have the sum of forces in the y direction is equal to 0. So let's go ahead and write those out. So we can say that the sum of the forces in the x direction is going to be equal to N1, which is positive to the right, minus N3, which is negative to the left, is going to be equal to 0. Okay, and that gives us right off the get-go that we can see that N1 is going to be equal to N3. Okay, and then secondly, we have the sum of our forces in the y direction must be equal to, we have N2 acting positive upwards, minus weight 1 minus weight 2 is going to be equal to 0. So when I look at these 2 equations, I have 3 unknowns. I do not know what normal force 1 is, I don't know what normal force 2 is, and I don't know what normal force 3 is. Weight 1 and weight 2 I can determine from the density and the volume of the spheres, and we'll get to that here in a second. But I have 2 equations with 3 unknowns. So I know I can't solve this system of equations because if I have 3 unknowns, I have to have at least 3 equations of equilibrium. So I must be missing something. A while ago I said that we can draw 3 different free body diagrams. So let's go ahead and jump into that. We can draw another free body diagram in which we just analyze particle 1, and we can draw another free body diagram in which we just analyze particle 2. Okay, so if I want to look at just particle 1, just steel ball bearing 1, I can draw my 2-inch ball bearing here, and let's go ahead and draw our free body diagram. So our free body diagram, once again, we have weight 1 acting downward, I have N2 acting upward, and I have N1 acting this way. But if I no longer include the 1.5-inch steel ball bearing, now I have to account for the contact force between the ball bearings. I have to account for the contact force between the ball bearings. So I have an additional internal force. I have an internal force which I'm going to label F, directed in this direction. So I have F acting on this ball bearing 1, the 2-inch steel ball bearing. Additionally, I can look at the 1.5-inch steel ball bearing and draw its free body diagram. So if I draw its free body diagram, it also is going to have a weight acting downwards. We have a weight 2 acting downward. It has normal force 3 acting this way. And in accordance with Newton's third law, if there is a contact force that is acting on the 2-inch ball bearing by the 1.5-inch ball bearing, there is an equal and opposite contact force acting on the 1.5-inch ball bearing from the 2-inch ball bearing. So once again, we have another force here, which is acting on the 1.5-inch ball bearing, and it is going to be equal and opposite, but the magnitude is still going to be the same. So this is also going to be some force F, and I'm going to label that they're going to have the same magnitude. Okay, and this is what I wanted to stop and talk to you about. So this is where we have 3 different free body diagrams. We have 3 different free body diagrams, and it's really easy to think to yourself, okay, for each individual free body diagram, I have 2 equations of equilibrium. I have the sum of the forces in the x is equal to 0, I have the sum of the forces in the y is equal to 0, and I have 3 different free body diagrams, so I have 6 equations of equilibrium. And that is not the case. That is not the case. In fact, that is false. And as it turns out, once again, what did our rule say? Our rule said that we have 2n, 2 times the number of particles for equations of equilibrium. So if we only have 2 particles, then we must only have 4 equations of equilibrium. 4 equations of equilibrium. So as it turns out, if I was to write, in fact, let's just go ahead and do it. If I was going to write all my equations of equilibrium from each of these free body diagrams, you're going to see that we don't end up with 6 linearly independent equations, and that's very important. We're going to talk about what that means here in a second, but we do not end up with 6 linearly independent equations. We end up with only 4 linearly independent equations. So, let's take a look at the 2-inch ball bearing. The 2-inch ball bearing, let's go ahead and write our equations of equilibrium. So if I have that the sum of my forces in the x direction, it must be equal to, I need to define a new term here. I need to define a term, or the angle of this, the force, or this action, this force act. So I'm going to call this theta, and I'm going to call this theta here as well, because once again, the force acting on particle 1, the 2-inch steel ball bearing, is collinear with the force acting on particle 2. So they're collinear, so they must be at the same angle with the horizontal. Okay, so I can say that the sum of my forces in the x direction is I have an N1, which is positive to the right, and then I have a F cosine theta, which is going to be negative to the left, is equal to 0. Okay, and then I have my sum of my forces in the y direction must be equal to, I have an N2, which is positive up. I have a negative weight 1, which is negative because it's downward. And then I have a negative F sine of theta, which is also downward. And once again, we're looking at this component, this downward component of F. So minus F sine theta is going to be equal to 0. Finally, let's take a look at the 1.5" steel ball bearing. So I can say that the sum of my forces in the x direction is going to be equal to a positive F cosine of theta minus a negative N3 is going to be equal to 0. And I have the sum of my forces in the y direction is going to be an F sine theta, which is positive because it's upward, minus W2 is going to be equal to 0. Okay, so this is where we kind of get into the linearly independent portion of this concept, right? Because we have 1, 2, 3, 4, 5, 6 different equations. 1, 2, 3, 4, 5, 6 different equations. So what I want you to notice is what happens if I take the sum of my forces in the x direction equation from particle 1 and the sum of my forces in the x direction equation for particle 2 and I add them together. What happens if I add them together? Well, I get an N1 minus F cosine of theta is equal to 0, and I get a F cosine of theta minus N3 is equal to 0. If I add these equations together, I have a positive F cosine theta, I have a negative F cosine theta. This goes away, and I end up with N1 minus N3 is equal to 0. Note that's the exact same equation for the sum of the forces in the x direction of the entire system. So we do not have what we call linearly independent equations. If I add the x equations together for my individual particles, I get the equation of equilibrium for the entire system. And if you do it the exact same way, if I add my y equations for my individual particles together, I get the y equation for my entire system. So I do not have independent equations. So let's kind of talk about what I mean when I talk about independent equations. Linear algebra is not a prerequisite for this course, so I'm just going to quickly run through this in the simplest way that I can kind of make it make sense. So let's say I have a two-variable equation. I have a two-variable equation, something like x plus 2y is equal to 4. X plus 2y is equal to 4. I can't solve this equation, or I should say that this equation has infinite answers. It has infinite answers. For whatever value I plug in for x, I will get a different value for y. So I have an infinite number of solutions to this particular equation. If I wanted to solve for one particular solution, if I have two variables, I need two equations. So if I was to have a second equation that was 2x plus 4y is equal to 8, you would say, okay, now I have two equations, two unknowns, and I can solve this system of equations. But that is not the case. Look what this second equation is. This second equation is just the first equation multiplied by 2. Just the first equation multiplied by 2. This equation is in fact the same as this equation, so I do not have what we call two independent equations. So this system of equations still has an infinite number of solutions because in reality, both of these equations are the same equations. That's kind of our first example of independent equations. Okay, now let's go ahead and take it up to another level. Let's look at a system of equations where we have three variables. Let's say I have something like x minus y plus 2z is equal to 3. There's my first equation. And now I have a 2x plus a y plus a z is equal to 2. Okay, I have three unknown variables. I have an x, a y, and a z. Okay, if I want to solve for a single solution for each of those variables, I need to have three equations for my three unknowns. But I only have two equations for my three unknowns, so once again, these two equations have an infinite number of solutions. Let's say I go ahead and I create a third equation, and my third equation is going to be 3x plus 0y plus 3z is equal to 5. 3x plus 0y plus 3z is equal to 5. So you would think to yourself, okay, I have 3 equations, I have 3 unknowns. But what's really happening here is I took these first 2 equations and I added them together to generate my third equation. So 2x plus x is 3x, negative y plus y is equal to 0y, 2z plus z is 3z, 3 plus 2 is 5. So even though I have 3 equations here, this last equation is not linearly independent. This last equation is some combination of these first two equations. This last equation is some combination of these first 2 equations. And you can do it in any kind of combination of these 2 equations that you want. So if I did something like 2 times the first equation minus 5 times the third equation will get me another equation, but it's still a combination of those 2 equations, and this last equation is not linearly independent. So because this last equation is not linearly independent, this system of equations will still have an infinite number of solutions. We'll still have an infinite number of solutions. That's an example of what we're talking about. So let's jump back into our problem. So we said, okay, we drew 3 different free body diagrams, and for each of our free body diagrams, we had 2 equations of equilibrium. We had 2 equations of equilibrium. So we would think, okay, we have 6 equations of equilibrium. But as it turns out, the 2 equations for our system as a whole are just the addition of these equations for each individual particle. They're just the addition of these equations for each individual particle. So both of these equations are, in fact, not independent of these 4 equations. So we only have 4 independent equations. So this is the big takeaway when we're analyzing system of particles, is that even though, for instance, when we have 2 particles, we can draw 3 different free body diagrams. In order to solve the problem, I only need to pick 2 of the different free body diagrams in order to solve the system of equations. So I can pick any 2 that I choose to analyze. I can either pick these 2 systems of equations, so these 4 equations, I can pick these 4 equations, or I can pick these 4 equations. I can solve it in any way, and I'm still going to get the same answer. So that's what we come down to. It doesn't matter which system of equations we pick, but we just need to pick 4 of these 6 equations. We need to pick 2 of the x equations and 2 of the y equations, and then we can then solve this system of equations. So, like I said, it doesn't matter. Just to be kind of consistent with your notes, I believe in your notes I picked this system of equations, or these 2 equations, and these 2 equilibrium equations. I did not use the equilibrium equations for the 1.5 steel ball bearing, so we're going to go ahead and erase these 2 equations, and we can write out the equations that we need to know. So, once again, from this free body diagram and this free body diagram, I ended up with 4 equations with 4 unknowns. We're going to call this equation 1, this equation 2. We have N1 minus f cosine of theta is equal to 0, and we have N2 minus W1 minus f sine theta is equal to 0. I'm going to go ahead and erase the free body diagrams so that we can start looking at these equations that we just determined that we need to solve. So, in this system of 4 equations, I have 4 unknowns. I don't know N1, I don't know N2, I don't know N3, and I don't know F. So those are going to be the 4 unknowns that we need to solve for. If I have 4 equations, 4 unknowns, I should have everything that I need to solve this problem. The only thing that I'm missing is I'm missing weight 1 and weight 2. Sorry, not just weight 1 and weight 2. I'm also missing theta, which is the angle with the horizontal that the contact force between the spheres acts. So I need to figure out weight 1, weight 2, and theta in order to solve this problem. So let's start with the weights because they're pretty straightforward. So it was given to us that the specific gravity, or the weight density, I shouldn't say specific gravity, but the weight density of the 1040 steel was 0.2834 pounds per inch cubed. So we said that the weight density of steel was 0.2834 pounds per cubic inch. 2834. Yep. we know the diameter of the spheres, so we should be able to figure out the weight of the spheres. If we know the weight density, then I can say that the weight is going to be equal to the weight density times the volume. So I need to determine the volume of the spheres. Well, the volume of a sphere is going to be equal to 4/3 pi r cubed. Hopefully you remember that from geometry, 4/3 pi r cubed. So we can say that weight 1, let's write that right here, V is equal to 4/3 pi r cubed. So weight 1 is going to be equal to 0.2834 pounds per cubic inch, times 4/3 pi. The radius of the sphere is just going to be 1 inch cubed, and this is going to be inches cubed. So my inches cubed are going to cancel out. I can plug all that into my calculator, and I get the weight of ball bearing 1 is in fact 1.187 pounds. 1.187 pounds. I can do the exact same thing for the ball bearing, the 1.5-inch ball bearing. So I get that weight 2 is going to be equal to 0.2834 times 4/3 pi. The radius of an 1.5-inch ball bearing is 3/4 of an inch, so 0.75 cubed, which is going to be in fact 0.5008. So now we know what the weights are in our equations. So I'm going to go ahead and go back to our system of 4 equations. I can move weight 1 and weight 2 over to the other side of the equation. So I can say that N2 is equal to weight 1 plus weight 2. So I get that N2 is equal to 1.187 plus 0.5008 pounds. So we have already solved for our first contact force. It's just a simple addition of 2 numbers. So we can go ahead and solve for that here in a second. Okay, let's go ahead and plug our weight 1 and our weight 2 into our other equation as well. I have weight 1, which appears down here in our 4th equation. It's negative. I can move it to the other side of the equation. So this becomes a into minus f sine theta was equal to weight 1. And we said that weight 1 was 1.187 pounds. So our system of equations is actually starting to clean up pretty quick here. Okay, now the next thing that we need in order to solve this, because once again, we've gotten rid of weight 1 and weight 2, but we only have 4 equations. We have N1, N2, N3, and F. I need to determine theta. So theta is a geometry problem in this case. We can determine theta by analyzing the geometry of the system. So the contact force between the spheres is going to be normal to the surface, the line of the surface where they contact, right? It's going to be normal to the surface where they contact. And you analyze spheres and cylinders and all round objects kind of the same way. So if I have my 2-inch ball bearing and I have my 1.5-inch ball bearing. If I have the center of my 2-inch ball bearing and the center of my 1.5-inch ball bearing, if I connect the centers of those circles, it will connect through the contact point. Of those centers. So, as it turns out, the contact force between them is going to lie along that line. So we're going to have the force acting on the 1.5-inch ball bearing along that line, and we're going to have the same force acting along that same line of action acting on the 2-inch ball bearing. So what it comes down to is we need to determine the angle of this line. So I'm interested in theta, which is going to be the angle with that line with the horizontal. So we are after theta. But how can we determine that? Well, we can determine that from the geometry. I know, let's go ahead and clean this up just a little bit. And let's start drawing ourselves a triangle. So if I have my line that connects the centers of my two circles, I know the length of that line because the length of that line is just the radius of the circles added together. So the length of this line is just going to be the 1 inch plus 0.75 inches. So I have 1 inch here, 1.0 inch, then I have the 0.75 inches here. So the length of this line is 1.75 inches. Okay? Now I need to determine kind of what other dimensions that I can determine from this particular triangle, right? So if I'm saying, okay, I want to determine what theta is, I can draw myself a vertical line here, and I get myself a right triangle. If I can determine either this distance or this distance, I can use my trigonometric functions in order to determine what theta is. And the easiest one to determine ends up being this length right here, which I'm going to call length L. I'm going to call that length L right there. And if I determine what L is, then the cosine inverse of the adjacent over the hypotenuse, so the cosine inverse of L over 1.75 will give me what theta is. Well, how can I determine what L is? Well, I can determine what L is back from the dimensions of our problem. They gave us that the width of the container is 3.2 inches. So the width of my container falls all the way from, if I draw a vertical line coming down from this contact point with the outside of the 1.5 inch steel ball bearing, and then it comes all the way to here to the outside of the 2 inch steel ball bearing. Well, I know what this distance is. This distance right here is just the radius of my 2 inch ball bearing, so I have another 1.0 inches here. And I know what this distance is here. That's also the radius of my 1.5 inch steel ball bearing. So this distance right here is also going to be 0.75 inches. So what I end up with is the fact that I know that this entire width is 3.2. So I know that 1.0 plus L plus 0.75 is equal to 3.2 inches. So now I can say, okay, if I determine all that out, I end up getting that L is equal to 3.2 minus 1 minus 0.75, which is, in fact, 1.45 inches. 1.45 inches. Well, now I know what L is. I know what my hypotenuse of my triangle that goes from center to center is. So I can say that the cosine of theta is going to be equal to adjacent over hypotenuse, which is 1.45 over 1.75. So I can say that theta is equal to the cosine inverse of 1.45 over 1.75, which is in fact 34.05 degrees. 34.05 degrees. So now I can go back to my system of 4 equations over here. So I got N1 minus F cosine of 34.05 degrees is equal to 0. And then I have that N2 minus F sine theta. So I have an N2 minus F sine of 34.05 degrees is equal to 1.187 pounds. So now we have our system of 4 equations with only our 4 unknowns in it. So we have gotten it down to a fairly straightforward system of equations. We can solve it any way that we want to solve it. We can solve it by using matrices, but because this N2 already simplified with just being able to solve N2 for one equation, let's just go ahead and solve it in order by hand because it's a pretty straightforward one to do. Okay, so we can say that from this equation right here, we got that N2 is equal to 1.688 pounds. Just by adding those two values together. Similarly, we can say, okay, this turns into N1 is equal to N3. Okay, that'll simplify things here in a minute, but I can take my value for N2, now I can go down and I can plug it into this equation right here, and I can say that N2, which is going to be 1.688 pounds minus F sine of 34.05 degrees is equal to 1.187. I can move my F sine theta over here. I can move my 1.187. I get the F sine of 34.05 degrees is going to be equal to 1.688 minus 1.187, which is in fact that same 0.5008 degrees. I divide both sides by the sine of 34.05, and I get that my contact force in between the spheres is in fact 0.8945. 0.8945 pounds. Okay, let's make sure we keep track. This was an answer to the problem. This is also the answer to part B of the problem. So this was an answer to part A. But now I can take this value for F, and I can go ahead and I can plug it into equation 3 over here. I can plug it into equation 3 over here, and I end up with, let's go ahead and just write N2 is equal to 1.688 pounds Okay, now I can use my F and my N1, so I get that N1 minus F, which is 0.8945, cosine of 34.05 degrees is equal to 0. So I get that N1 is 0.7411 pounds, which is also equal to N3, which we got from equation 1. So N3 is also equal to 0.7411 pounds. Okay, and now we have solved for everything that the problem asks us to solve. So we know what the contact forces on the left and the right side of the container are both 0.7411 pounds. The contact force with the ball bearing, the 2-inch ball bearing on the bottom, is in fact 0.688 pounds. And then we have the contact force between the two ball bearings we found to be 0.8945 pounds. I hope this kind of makes sense. The big thing I wanted to illustrate from this problem was how we can determine what our 4 equations were from 2 particles, and then I also wanted to make sure everyone understood the whole linearly independent side of this problem. It's really easy to think, okay, I can draw 3 free body diagrams and get 6 equations, but you actually cannot. For particle equilibrium, you can only have 2 times the number of particles. That's the maximum number of independent equations that you can find. Okay, so now we have worked a fairly simple particle equilibrium problem in 1 dimension. We worked one a little bit more complex in 2 dimensions. So let's go ahead and step it up to the final problem that we're going to work today. We are going to work one 3-dimensional problem. So let's go ahead and take a look at the diagram and read the question. It says, a 500-pound crate is suspended by the cables shown below. What is the tension in each cable? So they give us a diagram here. I'm going to try and just keep the diagram up on the screen because it's kind of challenging for me to draw it by hand. But we are going to go ahead and start taking a look at this, and they want to determine what the tension is in every cable. So what I'm going to look at is I'm going to look at 2 particular particles in which we are going to look at force equilibrium at those particles. We are going to look at the knot at point A, and we are going to look at the knot at point C. So we're going to look at the knot at point A, and we're going to look at the knot at point C, and then we're going to see that we're going to be able to determine the tension in these cables fairly straightforward. Okay, so let's start by looking at knot A. Let's start by looking at point A, knot A, particle A, whatever you want to call it. Let's start looking at the forces that are acting at particle A. So if we look at particle A, and specifically I want to look at the xz plane, because if I look at particle A in the y direction, which is kind of in and out of the page, there is no forces acting. The tension in all of the ropes are confined to the xz plane. So I can define, if this is my xz direction, I have my not at point A, I have a tension acting this way, which is going to be cable tension AB, I'll call it. And the problem gives us that tension AB is at a 20-degree angle. We have tension AC, which the problem gives is acting at a 35-degree angle. And then we have the weight of the 500-pound crate acting downward. So we have a 500-pound crate acting downward. So if I look at my free body diagram of point A, I have, in this case, it's a three-dimensional problem, but this particular point simplified into a two-dimensional problem. So in the two-dimensional problem where I'm confined to the xz plane, I have two equations of equilibrium, which is great because I have two unknowns. I do not know TAB or TAC. So let's go ahead and start drawing or start writing our equations of equilibrium. And we can start by saying that the sum of the forces in the x direction is going to be equal to a negative TAC cosine of 35 degrees plus a TAB cosine of 20 degrees is equal to 0. Okay, and I can say that the sum of my forces in the z direction must also be equal to 0. Well, I have a TAC sine of 35 degrees acting upward. I have plus a TAB sine of 20 degrees acting upward minus 500 is equal to 0. Okay, I can rewrite this last equation if I'm going to say that the sum of my forces is equal to 0, but I can move this 500 over to the other side of the equation. So I can say that this is going to be equal to 500, and now I have a 2x2 system of equations. I have a 2x2 system of equations, so let's go ahead and solve this. You can solve this any way that you want to solve it, but I'm going to go ahead and solve it using kind of matrices and linear algebra, and we can say that I have a negative cosine of 35 degrees, I have a cosine of 20 degrees, I have a 0, and I have a sine of 35 degrees, I have a sine of 20 degrees, and I have a 500 here. And if you recall from algebra, we can plug this matrix into our calculator, and we can use the reduced row echelon form function on this matrix. Once again, the order of our coefficients is important. So I have, this is my TAC coefficients, these are my TAB coefficients, and then these are my numerical, or my answer coefficients, however you want to call that. But I can plug this directly into my calculator, and it will solve this system of equations for me. And when I solve the system of equations for me, I end up getting that TAC is equal to 573.6 pounds. And I get that TAB is equal to 500.0. So, the problem asked for the tension in every cable, so we have found the tension in the first two cables, AC and AB, but we have additional cables, we have CF, CE, and CD that we need to solve for tensions in. In order to find those tensions, we need to jump over and do a free body diagram and a force equilibrium equations for the point C. For the point C. Now, point C is unfortunately not constrained to any two-dimensional plane. In fact, it's constrained to, or it's not, it's in all three dimensions. It's in all three dimensions. So let's go ahead and jump in and take a look at point C. So when we're working in 3 dimensions, this is going back to what we covered back in chapter 2, and we said forces directed along a line. So if we have a tension acting from point C to point D, that force T, the tension CD, acts along that line. So we need to be able to write the force vectors into Cartesian form. We want to write the force vectors into Cartesian form. So let's look at each of the individual tensions, like each of the individual ropes coming out of knot C, and let's go ahead and write them as vectors. Let's write them as vectors. So we'll start with TAC. So TAC, we already showed that it was limited to the XZ plane, so it only has forces in the X and the Z direction. So when I'm looking at the knot C, the tension acting on C, so we can draw C over here. That's C, and we can call this is going to be my X plane, this is going to be my Z plane, and then my Y plane would be going back into the board, while Y plane is going to be going back into the board. But TAC is in fact limited to the XZ plane, so we have a TAC acting downward, and the problem gave us that it is with a 35 degrees to the horizontal. It is acting at 35 degrees to the horizontal. So if this is going to be my X direction to my Z direction, I get that my TAC, or in this case, I want to be clear, I'm going to go TCA. TCA, it's going to be the tension from C towards point A, is going to be at a cosine 35 in the positive X direction. So I get TAC cosine of 35 degrees in the I direction. And then we have a minus a TAC sine of 35 degrees in the K direction. So let's be clear, this is the vector form. We're writing this in vector form, and I'm just going to assume that the coefficients for all of them you recognize are going to be the magnitude. So I'm not going to write the magnitude line every time. We're going to have the magnitude of the tension, but we are splitting it into its vector components. So we have a cosine 35 in the I and a sine 35 in the Z, in the K direction. Okay, let's take a look at TCD. So the vector of the tension that points from C towards D, in this instance, once again, we are confined to the XZ plane. We're confined to the XZ plane, and we have a rope. It goes up this way, and this is going to be TCD, and they gave us, from the dimensions of the rope, they gave us a slope triangle. So we have that it goes upwards 24 feet, and it goes over 10 feet. It goes upwards 24 feet, and it goes over 10 feet. So I can now say that, in this case, my slope triangle is going to be 24 and 10. I can use Pythagoras' theorem to determine what the length of the cable is going to be. So I do that 24 squared plus 10 squared. Square root of second answer is in fact an even 26. So now I have a slope triangle which is going to be 24, 10, 26. Okay? Now with the slope triangle, we don't have to do cosine of angles. We can just use the similar triangles method in order to determine our dimensions. So TC is going to be a 10 over 26 in the X direction, but it's to the left, so it's negative. So we have a negative 10 over 26 TCD in the I direction, plus a 24 over 26 TCD in the K direction. Okay, so now when we analyze both CEF, or CE and CF, we recognize that those particular cables are constrained into 2 dimensions as well, but they are no longer constrained to the XZ plane, they're constrained to the XY plane. They're constrained to the XY plane. So in this case, I'm going to say, the YZ plane, So In this case, I'm going to now draw another kind of diagram looking on edge of these two cables. So here's my point C, and we are going to have the y-axis directed to the left and the z-axis directed upward, and we have two cables acting downward. We have CE and CF, so we have TCE and we have TCF acting downward. Once again, they gave us slope triangles based purely off the dimensions of the cable. So we can say we have slope triangles based off the dimensions of the cable. Once again, the cables go a vertical distance of 24 and a horizontal or a y distance of 7, and both of them are the same. Both of them are the same, so they're both 24 and 7. So we can figure out what the hypotenuse or the length of the cable is what we need for our similar triangle. So we can say that 7 squared plus 24 squared, 7 squared plus 24 squared, square root of second answer. I get that this is a 25, and I already forgot that we're in feet. Yeah, 25-foot length. So once again, we have our slope triangles that we can use in order to use similar triangles. We don't have to use the sine or the cosine when we break TCE and TCF into vector components. But now we are in the we are in the YZ plane, not the XZ plane. So we can say that TCE is going to be equal to, we have a negative 7 over 25. Note that my positive y-axis is this way when I drew it with for a right-handed coordinate system. So for a right-handed coordinate system, my TCE is actually in the positive y direction. So I get a 7 over 25 TCE in the J direction, and then I have a negative 24 over 25 TCE in the K direction. I do the exact same thing for my TCF. So my TCF vector is going to be a negative 7 over 25 TCF in the J direction minus a 24 over 25 TCF in the K direction. So anytime that we're working three-dimensional particle equilibrium problems, this is always going to be the hardest part of the problem. The hardest part of the problem is going to be looking at the system, or looking at the physical system, and determining the vectors along which our forces act, So we did it this way by doing similar triangles, but we could have done it like we did a lot in Chapter 2, in which we went through and at each point, we could have said at each point like E, F, and D, we could have found the X, Y, Z location, we could have found the position vectors that pointed from point C to point D, point C to point E, and point C to point F. We could have found the position vectors, we could have divided the position vectors by the magnitude, and then we would have gotten the unit vectors, and we would have gotten the exact same thing. This is, in fact, the unit vectors multiplied by the magnitude. That's what we did here, but we just determined it analytically by analyzing the problem geometry this way than by actually going through and determining the points, finding position vectors, finding the magnitude of the position vectors, and creating unit vectors for each of those individual tensions in those cables. But anyway, this is the hardest part of this problem. Once we get to this particular part of the problem, it becomes pretty straightforward. We have 4 force vectors acting on particle C. We can break that into our 3 scalar equations of equilibrium, in which the sum of the forces in the I are 0, some of the forces in the J are 0, some of the forces in the K are 0. Now what we have here, you think, okay, Zach, we have 4 unknowns. We have TCA, TCD, TCE, and TCF. But recall that we solved for TAC in the first part of the problem. So we already know what this value is. Because we determined it previously from looking at particle A. By looking at particle A, we determined what this tension is. But now, the other big mistake that I see students I see students do all the time is they think that once they get to this point that they just go ahead and they solve this system of equations like the way it is. You may have these three equations for particle equilibrium, and you just put that directly into the matrix on your calculator and you try and solve that. That is not the case. Recall that you need to have your I's and your J's and your K's all separated into your force equation. So our next major step is that we need to break this into our three equilibrium equations. We need to break this into our three equilibrium equations. So we can say the sum of our forces in the x direction is going to be the sum of everything that has an I. So we have an I here, we have an I here, we only have J's and K's in these last two equations. So I can say that it is a TAC, or TCA, whatever you want to call it. We already solved for this value. Cosine of 35 degrees minus 10 over 26 TCD is equal to 0. Okay, next, we need to go through our equations and we need to sum our forces in the y direction. So the sum of our forces in the y direction is going to be equal to, and we go back to our equations or our vector equations, and we're looking for everything that has a j. Everything that has a j. So we end up with a 7 over 25 TCE minus a 7 over 25 TCF is equal to 0. So there's our equation 2. And then finally, we sum our forces in our z direction. So we need everything that has a k. So we have a k in all four of our vectors, so everything that's in the z direction. So we say that the sum of our forces in the z direction is going to be equal to a negative TAC sine of 35 degrees plus a 24 over 26 TCD minus a 24 over 25 TCE minus a 24 over 25 TCF is equal to 0. These are our three equilibrium equations. Please do not make this mistake. I see it all the time. In this case, it's pretty obvious because we ended up having 4 different forces acting on our particle equilibrium, but it's really common for problems to work in 3D in which you'll be looking at a particle and you may only have 3 forces acting on that particle, and students always forget to go from your force vectors. You have to then convert them into your equilibrium equations. Do not forget to convert your force vectors into your equilibrium equations. Now you can solve this system of 3 equations and 3 unknowns in any way that you wish. You can use matrices on your calculator, like I'll often show you how to do in class. But in this case, it kind of unravels pretty easily just to go ahead and solve it out by hand. So let's just go ahead and do that. Recall from the particle equilibrium of point B, we already found that TAC was 573.6 pounds. We already found that that was 573.6 pounds. So we can go ahead and just solve this equation for TCD. So we get a 573.6 cosine of 35 degrees is equal to 10 over 26 TCD. You plug this in your calculator, you multiply it by 26, you divide it by 10, and you get as simple that TCD is in fact going to be 1,222 pounds. 1,222 pounds. Okay, this second equation looks a lot like we did in our last problem. We had the 7 over 25, we had the same coefficient for both, so this one actually simplifies to TCE is equal to TCF, which makes sense when I look at the problem. It is symmetric, so I'm not surprised that the tension in those two cables is the same. So that's a pretty straightforward thing to do. But now we know all of that, and we can plug everything into this bottom equation, and we can just combine TCE and TCF into the one unknown that it is. So we get that a negative TAC, which we said was 573.6, times the sine of 35 degrees plus 24 over 26. TCD we just solved for, it's 1,222. 1,222 pounds minus, we have a 24 over 25 minus a 24 over 25, but TCE and TCF is the same. So we have a minus 2 times 24 over 25. TCE is equal to 0. I know everything in this equation. It just becomes an algebra problem from this point out. I can go ahead and solve this algebra problem, and I get that TCE is equal to 416.0 pounds, which is also going to be equal to TCF. So we were able to solve for the tensions in the last three cables. So by analyzing particle A, we were able to determine the tensions in AC and AB. And then by analyzing particle C, we were able to solve for the final three tensions, which was in rope CD, and then ropes CE and CF. So we were able to find every tension in this problem, or every tension in all of the cables, which is what the problem was asking for. So that is where we're going to end it for today. I hope those three problems were helpful in kind of illustrating how we analyze particle equilibrium. So once again, I apologize for being out of town this week, but I did have some stuff that I had to take care of. So thank you for tuning in and watching the video lecture. So because you made it to the end of the lecture, what we are going to do for today's reading quiz, because I do have a reading quiz for every day that we meet for class. So for today's reading quiz, I want you to send me an email, and in the email I want you to say Chapter 3 Additional Problem Reading Quiz, and in the body of the email me the answer to the following problem. 2 plus 3 is equal to what? 2 plus 3 is equal to what? Go ahead and email me that, and I will give you your credit for today's reading quiz. So thank you so much. Please do not forget that you have a test that is going to be on, this is static, so it should be on Wednesday. So we will not meet for class on Wednesday because you will have an exam over chapters 1, 2, and 3. All of this material that we just covered will be on exam, the first exam. So please make sure you finish your exam on Wednesday.